Now we're going to talk about P and NP, the two major classes of problems that form the basis for the theory of intractability. And so we talked about search problems, and what we're going to do is just name that class of problems, and that's what we call NP. NP is the class of all search problems. Now I just want to mention again that the classic definition that's often used in many books and papers that you'll read about this topic, the classic definition limits NP to yes-no problems. But again, the major conclusions that we draw are exactly the same. So we just listed a bunch of problems that are in NP. And the way that we know is we had a very concrete definition of what we mean by a search problem. You have to be able to, given a solution, you have to be able to verify in guaranteed polynomial time that you have a solution. And the four satisfiability problems that we considered and factor all are in the class NP. So we're using the concept of a search problem to classify some problems. One way to think of NP is it's really what we would like to be able to compute. We'd like to have algorithms that solve all of these problems. And it's a very, very general class of problems. It's almost articulating in as general a way as possible what we mean by a problem that we want to solve computationally. So these are the problems that we'd like to solve. Some of them we know how to solve, some of them we don't. That's NP. Now, by contrast, there's another class, P, where we add a restriction, and that's the class of search problems that we know how to solve in polynomial time. So that is, we have generally we proved that a problem's in P by demonstrating an algorithm that is guaranteed to run in polynomial time for any instance of that problem. And again, the classic definition is about yes-no problems. So here's a bunch of problems that are in P. And so we already showed LSolve because Gaussian elimination runs in polynomial time. And we already talked about LP because Kachin's algorithm works for linear programming. And then pretty much all the algorithms that we've covered in this course are cast as search problems and also have polynomial time solutions. We've been talking about programs that are polynomial time solutions, and just a little bit has to be done to convince yourself that, or to cast the problem as a search problem. And many of them are explicit search problems, like ST connectivity. You're searching for a path in a graph, and Theseus and the Minotaur, showed if you are given a path, you can check that it's a path easily, so it's a search problem. So P is the class of search problems that can be solvable in polynomial time. So the significance of P is those are the ones that we actually do compute feasibly. So NP is the ones, all the ones we would like to, and P is all the ones that we actually do compute feasibly. And those are perfectly well-defined classes of problems. Now, what is the N and NP for? Well, just a brief moment to talk about that. The N and NP stands for non-determinism. And the idea of a non-deterministic machine is one that can guess the desired solution. And that's an abstract machine. As far as we know, we don't have non-determinism in real-life devices. But it's fine to have an abstract machine of that sort. Remember, for our implementation for regular expression pattern matching, the way that we solved that practical problem was to imagine a non-deterministic machine and then write a program that would simulate that machine by trying all different possibilities. And in fact, that whole exercise really gets at the difference between polynomial and exponential time. first approach is a naive approach to simulating that machine turns out to be an algorithm that can run in exponential time for some inputs, and we actually saw that today there's implementations like that out there that hackers can exploit to deny service. The implementation we show had guaranteed polynomial time. So non-determinism was an abstract device that we used to help us try to get to a real practical solution, and that's what we're doing again. So let's imagine we have a non-deterministic machine that can guess the solution. So like if you're in a deterministic machine, if you make an array and create an array of size n, then Java, we know deterministically initializes the entries to all 0. But what if that array A is supposed to be our solution to a integer linear programming problem? We could have a non-deterministic machine initialize the entries to the solution. It could just guess what the right answer is and initialize it. So it seems like a really, really powerful capability. For example, for integer linear programming, we could just tell the non-deterministic machine guess the solution and we'd be done. And the same concept goes all the way down to a Turing machine. The whole idea of a finite state machine or of any computation that people think about is the machine's in some state and it's fully determined what the next state will be. And Turing machine's the simplest type of imaginary machine with that kind of capability. But it's very simple to make a Turing machine non-deterministic the same way that we made finite automata non-deterministic. You just let it go to more than one possible state. So when you think about non-determinism in this way, it's pretty clear almost immediately that NP is the class of search problems that are solvable in polynomial time on a non-deterministic Turing machine. Even if the machine gives the solution, what we're requiring is that we have to be able to check that it's a solution in polynomial time. And that's NP. So what we are led to immediately is what's called the extended Church-Turing thesis. And that's the idea that P is the ones that we know how to solve, but it's the class of problems that we're ever going to be able to solve in the natural world. And again, the evidence for supporting the thesis is that all the computers that we know about, we simulate them in polynomial time. People wondered, and have wondered and still wonder, is it possible that there are computers out there that work differently or more efficiently than the computers that we've built? Here's an interesting and simple example. There's a thing called a Steiner tree, which is like an MST, except you're not restricted to have your lines go through the points that are given. Steiner tree, you're given some points, and what you're supposed to do is find a set of lines of minimal length that connect the endpoints. Now, there's quite a bit of math and geometry even to prove that a given set of lines is a Steiner tree, but like for 4 points, it's known like this in a rectangular array. That's what the Steiner tree looks like. Can we write a program to compute Steiner trees? It's a search problem. Although it's not completely easy to characterize as a search problem, but it is. But anyway, the point for now is that people wondered, actually, if you put soap in between two glasses, the film formed by the soap, or soap bubbles is another way to think about it. But this is making it two-dimensional. If you put 4 points and put soap, and people have done this experiment, that's a photo off the web, you get a Steiner tree. And who knows what kind of computation is involved to make that. If you put lots of points, people have done, I don't know what number, but they can get Steiner trees for substantial numbers of points. Can we really compute Steiner trees that way? Well, you can construct things where it doesn't actually get the actual Steiner tree, so it doesn't really work. And that's just one example of an attempt. There's plenty of other examples out there. But the extended church-Turing thesis hasn't been with us for as long as the church-Turing thesis, and maybe it's not quite as strong, but it's held for quite a long time. And people are assuming that there's not going to be a design that's going to make the difference between polynomial time in this natural world. If we're going to make future computers more efficient, we're just going to improve our existing designs. That's the extended church-Turing thesis. But it leaves us with, all of this leaves us with the basic question, does P equal NP? So P is all the problems we can solve in the natural world, NP is all the search problems we'd like to solve. If we had non-determinism in the natural world, do we have non-determinism in the natural world? Does non-determinism help? That's the question, does P equals NP? This question's been around for a long time and has even made it into the popular culture. And I think it'll make it into the popular culture much more when we start having, because we're starting to have massive online courses where many more people are learning about these fabulous concepts. Here's another way to think about P versus NP. It's like the idea of automating creativity. It's one thing to be creative, it's another thing to appreciate creativity. So Mozart comes up with a piece of music. Once that thing is created, we can appreciate it. Or Andrew Wiles proves Fermat's last theorem, and however he came up with it, there's a way to check it. Somebody can check it. Or somebody designs an airfoil or an airplane wing, we can verify that it has the properties that it's supposed to. Or Einstein proposes a theory, somebody can validate it. So there's the creative. Let's make something or come up with something. That's the analog to that is a solution to a problem, a search problem. And the ordinary thing to do is to check it. But if P equals NP, there's no difference. It's really like automating creativity. That's the computational analog to P equals NP question is a computational analog to automating creativity. Is P equals NP? That's the central question. Can you always avoid brute force searching and do better? For search problems, since we have a small solution that can be checked in polynomial time, there's always a exponential time solution, which is try all possible solutions. But that's not the question. Is can you always do better than that? That's the really the essence of the P equals NP questions. So there's two possibilities. If P is not in, so P is a search problem, so it's certainly in NP. Any problem in NP is also in P. So the question is, are there some search problems that we can't solve in polynomial time? So if the answer to the question is yes, then all the problems that I've mentioned that nobody knows the solution to, despite people working on them for many decades, if P is equal to NP, there's polynomial times algorithms for those out there. We just haven't found them yet. If the answer to that is no, that's really something fundamental about our universe, something that says something profound about the power of non-determinism. Non-determinism. If P equals NP, non-determinism actually doesn't help P not equal NP. It would. Now, the overwhelming consensus is that P equals not equal to NP, and we'll talk some more about some reasons that people believe that. But thinking about it, you can really convince yourself that it really seems as though having a machine that can, when you initialize an array, initialize it with solution to integer linear programming problem, really would seem that a machine like that is going to be more powerful than the machines that we're using. And that's why people believe that P is not equal to NP. But the frustrating thing is that theoretical computer scientists and mathematicians have been working on this for many, many years, and no one has been able to prove it. Actually, there's the Millennium Prize. You can earn $1 million from the Clay Mathematics Institute if you resolve P equals NP. Actually, there's other math problems on that list, but people who know algorithms, first of all, you could earn way more than $1 million if you resolve this problem. Second of all, if you're expert in algorithms, there's lots of other ways to earn $1 million. So it's not about the $1 million, it's about, this is, some would argue, one of the most important open mathematical questions that faces us right now.